the second part of section 5.6, we want to take a look at the three-dimensional version of centers of mass, moments, and inertia. We'll go through this example. The formulas are much like what they were in 2 dimensions, and we'll begin by drawing off the region in maple. Here's the x equals y squared. Here is the plane x equals z on the same coordinate system. Here's the xy plane, or z equals 0. And in green, the vertical plane x equals 1. So we'll magnify and isolate our region, and you can kind of tell that this in here is what we're trying to find the center of mass for. Now, perhaps sometimes I can show you the maple file that generated this, and we can actually twist and turn our solid object to see what's going on. But what we notice here is that if we were to pass a line through this green region, it would go through and come out here in this, I don't know, yellowish, greenish region. And so this is not, that's a line that's parallel to the x-axis. So this is not an x-simple region. Now you can tell, and again 3-dimensional drawings are a little tough to visualize, but if we were to pass a line through from the top, it would go in and come out the bottom. So this thing is z-simple. Now it could be y-simple. If we were to pass a line through this blue side here, it would go straight across and come out the other side. It would be parallel to this plane, this xz plane, the yellowish plane. And so because of that, even though it's going from blue to blue, it would still be y-simple. So we'll just begin our integration with the z's. I was showing you earlier the bottom of this object down here is on the xy plane, and the xy plane is z equals 0. The yellowish top on here is the plane x equals z. So any line drawn straight down parallel to the z-axis here, a line drawn straight down through there will intersect the plane x equals z and the plane z equals 0. Now in order, bottom to top, that would be from 0 to x. So that's the limits on our z integration. So I have just twisted that around so that we're looking straight down the z-axis. So what we see here is the projection of that solid onto the xy plane. And you can see what we've got is that we could either let our x's go from parabola to line. That's here. Here is a typical x from parabola to line. Or we could even let our y's go from bottom of parabola to top of parabola. I kind of like the idea of the x's, however. So we will use the x's going from parabola to line. Now that parabola we have right here, the value of x is y squared. And that line right there has a value of x of 1. So the strip that we have here will be going from parabola to line which would be, if we do dx next, from y squared to 1. And then, as you can see, if we did that, then the y value here at the bottom would be -1, and the y value at the top would be +1. So there's our setup for our integral. As we did with 2 dimensions, the constant here just means we have a constant density, so we use a k for that. Now, I won't take the time to evaluate this integral. You could do that by hand or with a calculator. And that comes out to be just a 4/5 k. Now, to find the moments, just like with the lamina, we will take this exact same triple integral, and if we want the moment about the xy plane, it has the same meaning as we did with the lamina. The moment about the xy plane means we need the distance from the xy plane. Well, the distance from the xy plane is z. So we take this exact same integral, insert a z, and again, however you choose to do the integral. Likewise, the moment about the xz plane means we need to insert the distance from the xz plane. Distance from xz would be y. And finally, the moment about yz plane, we insert the distance from the yz plane. Now later, I'll have all of these formulas on a single page for you if you want something to print out or write down. But our formula looks like this. Notice the similarities. The x-coordinate for the center of mass is the moment about the yz plane. Notice the y and z has no x in it, divided by the mass. So all of these are divided by the mass. And as you can see, the y bar has a moment about the xz, and the z bar includes the moment about the xy. So again, we just do those divisions, just make sure you get them in the right order. So now we're going to turn our attention to finding the moments of inertia. If you remember, the moments of inertia were very similar to the first moments in that they have to include the distance squared, this time from the respective plane. So if we want the moment, the inertia about the xy plane, it's just like the moment about the xy plane. We've got the distance squared, and the distance from the xy plane is z. Likewise, the other inertia, moments of inertia, would look like this. Now those are the moments of inertia about a plane. We're oftentimes asked for the moments of inertia about an axis. So again, here's the relationship. The moment of inertia about the x-axis is the sum of all of the second moments that contain x's, which means xy and xz. Likewise, the moment of inertia about the y-axis would be the sum of all the second moments that contain y, which would be xy and yz. And finally, the moment of inertia about the z-axis is the sum of the moments of inertia all containing z's, which would be ixz and iyz. And as promised, here's a listing of all of the formulas that we just used.